Question 11a. So let's start this off by graphing where z is 1 minus root 3i, so we're across 1 and down root 3. So z's there. And the argument, well, we can see that it's negative. And the way that I remember the special angles is that I actually just remember that root 3 is about 1.7, and then I draw it sort of accurately and eyeball this. So this looks like 60 degrees. So we know it's one of the special ones, so it's going to be that. Or 60 degrees is pi on 3. So the argument of z is negative pi over 3. For part 2, you might think, okay, let's work out what z over w is, but that's going to be kind of messy and not easy to work out the argument of. So instead what we should do is work out the argument of z and subtract the argument of w, because when you divide complex numbers, that'll subtract the angles. So the argument of z is negative pi on 3, and then the argument of w, so w is 1 plus I, which is up here. And you can see that that's on an angle of 45 degrees, or pi on 4. So we're subtracting pi on 4. And then let's just put them over a common denominator. This one's 4 pi over 12, and that one's 3 pi over 12. So we've got 4 pi, and 3 pi is 7 pi over 12. So that's the answer to 2. Part B. So you might have memorized some way to work out the slope of the asymptote from these values. But what I would do is just think about the behavior of y as x gets really big. So let's just solve this for y. And then as x tends to infinity, as it gets bigger and bigger, this gets really big, so the minus 1 is kind of insignificant, and you can just ignore that. So y squared on 4 tends to x squared on 12. Y squared tends to x squared on 3, and then we can just take the square root. And we're interested in the positive square root because we're positive y values. So we get that. So that'll be the equation of the asymptote, that y equals x on root 3. And then we can just do, tan of alpha is 1 on root 3. And that would give alpha equals 30 degrees, or pi on 6 radians. Part C. Okay, so we want angles between minus pi on 4 and 0. So minus pi on 4 is out like that. So we're interested in z between these two lines. And for this one, you want to think of this as being z minus 1 minus I. So that means the distance between z and 1 minus I is less than or equal to 1. So 1 minus I is there, if that's 1, and that's minus I. And we want the distance between z and this point to be less than or equal to 1. So that gives a circle with radius 1 around that point. And then we're just interested in points that are within that circle, because it's radius less than or equal to 1, and within that range of angles. So that's this. Part D. So the t formula for cos is 1 minus t squared over 1 plus t squared. That's what we'll be replacing the cos with. And then we've got to differentiate this so that we can work out what to replace d theta with. So dt by d theta. The derivative of tan is sec squared, and then you've also got this half inside here, which is going to come out the front. Okay, and then the problem we have is that we need to put this in terms of t, because we don't want to have any thetas when we do the integral. So if you remember, sec squared is tan squared theta plus 1. So that's going to make half of t squared plus 1. And then we want to solve this for d theta, so multiply both sides by d theta and divide by all of that. And that'll give d theta is 2 over t squared plus 1 times dt. And then we also got to work out when theta is 0 and 2 pi on 3, what's t? So theta equals 0 will give t is tan 0, which is 0. At 2 pi on 3, you'll get t is tan half of that, which is pi on 3, and that makes root 3. So we have the integral from 0 to root 3 of 1 over 1 plus 1 minus t squared on 1 plus t squared times the d theta, which is this. And then we just need to simplify this. So this is actually going to make the denominator much simpler when we multiply that, because that'll get rid of this. It'll cancel with that. So that times the 1 makes t squared plus 1, and then you've got this times that. Those just cancel, and you get 1 minus t squared. And then that cancels with that. And then this makes 2, so that actually cancels with that. So this whole thing just equals 1. And then integral 1 dt is just t from 0 to root 3. So that'll be root 3. And that's the answer. Part A. So imagine this region rotating around the x-axis and sweeping out a shape that's going to look something like this, except that I've cut this one into cylindrical shells. So the real one will be smooth. Obviously it won't have all these little steps. But the idea is that we imagine it like this, and we can add up all the volumes of the little shells, and that will give us the volume of the shape, but then we sort of think about the limit as the thickness of each shell tends to 0. And you can actually do this integral in 2 different ways. You can consider them to be disks, a bunch of disks stacked on top of each other, which is really what the diagram looks like. But what I meant it to be is a series of shells that fit inside each other like this. This is how they want us to do the integral, because they said use the method of cylindrical shells. So I've just highlighted one of the shells here and pulled it out, so you can see how I actually intended this diagram to look. It's not meant to look like a bunch of disks, it's meant to look like a bunch of cylindrical shells that are fitting inside each other. So what we need to do is work out the volume of the shell. You've got a radius here of y, and the thickness of each shell is whatever change in y we choose. And we have to work out the height as well. So if we go back to this diagram, it's as if we're taking like a little section of that and then rotating it around. That's what creates the shell. And we're trying to work out that length. So that'll be the x value there minus the x value there. So what we have to do is solve this for x. That gives x is 3 minus y. So that's that one. And this gives x is y on 2. So that's that x value there. So that distance will be the 3 minus y minus the y on 2. Which, if we simplify that makes 3 minus 3y over 2. So the volume of this shell, if you kind of imagine cutting it and like unrolling it, which we can kind of do because the shell is so thin that'll be sort of approximately the same volume if we cut it out and unroll it and make it into this flat rectangular prism thing. So the 3 minus 3y on 2 is that. That dimension is the delta y. And that length will be the circumference here, which is 2 pi r. So the volume of this shape, which is approximately the same as the volume of this shape, and we'll get more and more close to it as delta y gets smaller, that's going to be 2 pi times, and the radius was y, times that one, times the delta y. And when we add all those up and take the limit as delta y tends to 0, the way we write that is integral 2 pi y 3 minus 3y onto dy. So the delta y tends to dy when we take that limit. And this will be, y is varying from 0 up to 2. So that's the limits on the definite integral. So that'll be the answer, just that. Part F. We'll need to differentiate that so that we know what to replace the dx with. And that will give us, we have to use the chain rule there because it's like sine theta squared. So that'll give you 2 sine theta times the derivative of sine theta, which is cos theta. And then we can rearrange that. So dx is 2 sine theta cos theta times d theta. And then we need to work out what theta equals when x is 0.5. That will give us, so 0 equals sine squared theta. Solution of that will be theta equals 0. For x is 1/2, you'll get 1/2 is sine squared theta. We want to use the positive square root. So, normally it would be plus or minus root 1/2. But we want to pick like the first positive value of theta that will solve this. So let's just take sine theta as 1/√2, which gives pi on 4. Okay, so this integral becomes integral from 0 to pi on 4 of root sine squared theta on 1 minus sine squared theta times the dx, which we showed was 2 sine theta cos theta d theta. So let's simplify this a bit. We can turn the 1 minus sine squared theta into cos squared, and then because we're taking the square root, that'll be sine theta over cos theta. Ordinarily, it would be the absolute value of sine theta over cos theta, but because we're just going from 0 to pi on 4, we're just sticking in the first quadrant, so it doesn't really matter. They'll be positive anyway. And then we can cancel that, so we get integral from 0 to pi on 4 of 2 sine squared theta d theta. Now, how do we do that integral? Well, what we need to use is the fact that cos 2 theta is 1 minus 2 sine squared theta. So you can rearrange that and get 2 sine squared theta is 1 minus cos 2 theta. Now that is much easier to integrate than that, so we'll use that instead. And that'll give us, integrate the 1, that makes theta. And then that'll be sine 2 theta over 2. And then we're going from 0 to pi on 4. So let's plug the pi on 4 in. We get pi on 4 minus, so 2 theta is pi on 2, and sine of that is 1. So we get 1/2. When we plug in the 0, we get 0 there, and also sine of 0 is 0, so it's just that. That's the answer. Alright, that's it for question 11. So let me know if there was anything that didn't make sense to you, and stay tuned, because next time I'm going to be doing question 12.